Hey guys, induction proofs that involve inequalities is considered by many students to be the worst case, the most difficult case. We're going to go through two examples which are on the higher tier, the higher level, the most difficult types of exercises in order for you to be put in a good position for your school assessment or for the actual IB exam, for the real IB exam. So these are induction proofs that involve inequalities. The first example will have factorials in it, which makes it a little bit more complicated. And on the second one, which is, I think, a little bit worse, it involves binomial coefficients. So let's go through these two cases so you can aim for a 7 in your IB assessment. All right, so the first example is prove by induction that 2n factorial is greater than or equal to 2 to the n times n factorial squared for all positive integers. Now, we have 5 steps in every induction proofs exercise. I keep saying the same thing. It's always the same 5 steps. You have the propositional function, you have the base case, the inductive hypothesis, the inductive step, and then the conclusion. The first 3, no excuses. They're not hard. 30% of the marks are there. There's no excuse for you not to score those marks. Of course, we don't want to score only 30% of the marks, but still 30% of the marks are there. The fourth step, which is the inductive hypothesis, will be a little bit more complicated, especially if you're talking about proofs with inequalities. And the fifth, well, it's just the conclusion. You just have to vomit the same sentence, the same phrase that you use in pretty much every induction proofs. So it will get more complicated in the fourth step. So number 1, let's state the propositional function. We're pretty much rewriting what we need to prove, what was given to us by the exercise. And number 2, step number 2, is to prove the base case. Now, given that we're talking about positive integers, the number that you need to use to test is 1. 1 is the first positive integer. Therefore, you're going to test it on the left-hand side. You're going to substitute it on the left-hand side and on the right-hand side as well. So on the left-hand side, you have 2 times 1 factorial, which is 2 factorial, which is equal to 2. And on the right-hand side, you have 2 to the first power times 1 factorial squared, which is equal to 2 times 1, which is also equal to 2. Now, we just proved that, well, the left-hand side is greater than or equal to the right-hand side, which is what we expected. Therefore, the base case holds. Step number 3, the inductive hypothesis. We're pretty much copying P of n, but substituting every n that shows up for a k, and also inserting the following sentence. Assume that this is true for some positive integer k. Now let's get to the inductive step, number 4, p of k plus 1, which is what we want to prove. We want to get to p of k plus 1 starting from p of k. Now what is p of k plus 1? We're taking this inequality and substituting k plus 1 whenever we see a k there. So we have 2 times k plus 1 factorial greater than or equal to 2 to the k plus 1 times k plus 1 factorial squared. Now this is the part that induction proofs with inequalities starts to get a little bit tricky. But if you remember the following diagram, you're going to be fine. But before we get to the diagram, let me just state that in order to get to p of k plus 1 in an induction proof which involves inequalities, what we need to do is to start at what we're assuming to be true. So we're going to start here, and the goal is to get here. So the goal is to get here, starting from p of k. Now the diagram is the following. Let's say you're dealing with an inequality and you have a bigger side and a smaller one. So let's just picture a few numbers here. Let's say that this is 3 and this is 2, represented by the little squares, right? If 3 is greater than or equal to 2, which of course it is, if you change this 2 to a smaller number, meaning if you take the smallest side and make it even smaller, or you take the biggest side and you make it even bigger, then you get to keep your inequality. You're not breaking the inequality. That's why this type of induction proof sounds confusing or tricky, because you keep replacing things or placing things in the inequality but without breaking the structure, without breaking the inequality, which seems like they were taken out of nowhere. But there's a process behind it, there's a logic behind it. And that's what we're going to do. We're going to start with P of k, and we're going to manipulate this inequality without breaking it. Do know also that if you multiply the whole thing, the whole inequality by the same number, so for example, if you have a 3 here and a 2 here, and you multiply this number by 2 and this one by 2, the inequality still holds. Therefore, multiplying an inequality by a positive integer or by a positive number, any positive number, doesn't break it. Now, what should we multiply this by in order to get here? First of all, let's see what's inside the left-hand side. We have 2 times k plus 1 factorial, which is the same as 2k plus 2 factorial. And over here, on the right-hand side, we have 2 to the k plus 1, which can be rewritten as 2 to the k times 2 times k plus 1 factorial to the power of 2, which, of course, can be rewritten as k plus 1 factorial times k plus 1 factorial. Now let's see where we can begin. We can either convert this into this by making appropriate substitutions and inserting terms, or we can make this into this. And in this case, it is better to take care of the higher factorials, meaning the left-hand side. What's missing for us to go from here to here? Given that 2k plus 2 factorial is the same as 2k plus 2, 2k plus 1, 2k factorial, what we can do is to multiply both sides so we don't break the inequality by 2k plus 1, 2k plus 2. And again, as we do so, we get 2k plus 2 factorial on the left-hand side. It might be hard to see why multiplying by 2k plus 1 and 2k plus 2 would turn this into a 2k plus 2 factorial, so let me use numbers to illustrate that. If you take 4 factorial, for example, which is 4 times 3 times 2 times 1, and you multiply by 5, what you get is 5 factorial. And if you do it again, multiplying by the next integer, you get 6 factorial now. So that's exactly what is going on the left-hand side of the inequality. So let's keep going. This is greater than or equal to 2 to the k times k factorial squared times 2k plus 1, 2k plus 2. Given that the left-hand side is done, all we need to worry about is the right-hand side. And whenever you try to make any substitution, remember that in this case, the right-hand side is the smaller one. So if you want to replace any term in here by something, it has to be by a term which is even smaller. You cannot substitute it by a term which is greater than one of the terms that are already here. I'm going to write this k factorial twice, meaning k factorial squared, just so we can spot something that can be replaced. And also, this guy will be written as 2 times k plus 1. Now, consider that you have 2 to the k times 2. We already created this 2 to the k plus 1, which should appear in our solution as well. And let me write what's left so we can continue. Now, what is the next appropriate substitution that we can do? Well, on the right-hand side, we want k plus 1 factorial to show up twice. One of them is already here. If you consider, for example, that k factorial times k plus 1 is already k plus 1 factorial, we can already rewrite the right-hand side as such. Now, if we only had k plus 1 over here, we could multiply it by k factorial and get our k plus 1 factorial. Now, what we have is 2k plus 1, not k plus 1. So the question is, can we replace this guy by k plus 1? And the answer is yes, we can, given that k plus 1 is less than 2k plus 1. And we're talking about the side of the inequality, which is the smallest one. So we can always substitute it for something that's even smaller, giving us this result. Now, all we gotta do is to combine these terms and rewrite it as k plus 1 factorial, which gives us exactly what we were looking for. Now, we know that 2k plus 2 factorial is the same as this, and this is the same thing as this, but given that this p of k plus 1 is where we're trying to get, we can rewrite this inequality as such. It will make it clear to the examiner that we got to where we were looking for. And there we go. This is our final part of this calculation. Now, the fifth step in an induction proofs exercise is to state the conclusion. Given that p of 1 is true and p of k plus 1 is true whenever p of k is true for some positive integer k, then by the principle of mathematical induction, p of n is true for all positive integer n's. Now, here's the second exercise. It's one that involves binomial coefficients. Prove by induction that 2n choose n is less than 2 to the 2n minus 2 for all positive integers greater than or equal to 5. Dealing with binomial coefficients in an induction proof makes it not trivial. Now, if you add to that the fact that you have an inequality, well, you just made a very interesting exercise indeed. But let's take it step by step. Number 1, let's write the propositional function. We want to prove that 2n choose n is less than 2 to the 2n minus 2 for all positive integers greater than or equal to 5. And given that we're talking about positive integers which are greater than or equal to 5, then the base case should involve substituting 5 into n, both in the left-hand side and on the right-hand side. So on the left-hand side, what we have is 2 times 5, choose 5, which is the same as 10 choose 5. This is equal to 252. On the right-hand side, we have 2 to the 8, which means 256. Now, indeed, the right-hand side is greater than the left-hand side, which you can write like this. Therefore, the base case holds. Now, on to step number 3, also an easy step. We're going to assume that 2k choose k is indeed less than 2 to the 2k minus 2. And we're going to assume that that is true for some positive integer k greater than or equal to 5. Now let's get to the hard part, which is the inductive step. We're going to rewrite p of k, however, substituting k plus 1 in all of these cases in order to get to p of k plus 1. So 2k plus 1 choose k plus 1 should be less than 2 to the 2 k plus 1 minus 2. Now there's an even better way of writing this, which is to replace this by 2k plus 2, foiling the 2, and this guy by 2k. As you know, when we deal with induction proofs with inequalities, we start from p of k. And by manipulating this expression, we should get to this or to this, which is the same thing. How do we manipulate it? Well, by not breaking the inequality, meaning that you only substitute smaller things in the smallest side and bigger things on the bigger side. Now I rearranged everything here so everything fits. So that's why this page looks a little bit different now. So instead of thinking about these binomial coefficients, well, as binomial coefficients, we can convert everything to factorials, meaning that on p of k, which is our assumption, we have 2k factorial over k factorial, 2k minus k factorial. Given that, of course, the formula for a binomial coefficient is p factorial over q factorial, p minus q factorial. And this can be simplified to 2k factorial, over k factorial times k factorial. Therefore, we can rewrite our p of k as such. Now, where do we need to get? We need to get to p of k plus 1, which is right here. And we also have a binomial coefficient, which is on the left-hand side, which can be simplified using, of course, the same formula. So we have 2k plus 2 factorial over k plus 1 factorial, 2k plus 2 minus k plus 1 factorial, which can be simplified to 2k plus 2 factorial over k plus 1 factorial times k plus 1 factorial again. In other words, from here, we need to get to 2k plus 2 factorial over k plus 1 factorial squared being less than 2 to the 2k. Remember that the right hand side of p of k plus 1 is 2 to the 2k. Alright, so let's do it. Let's see what we can do with this. Remember that the idea is to go from p of k to p of k plus 1. So that's why I wrote them one on top of the other. So we need to get from p of k to p of k plus 1. Now, how can we get there? Similarly to the other example, we have over here 2k factorial times 2k plus 1, 2k plus 2. Therefore, in order to make this show up, we need to multiply both sides of the inequality by 2k plus 1 times 2k plus 2, giving us over here our 2k plus 2 factorial. So just to restate it, we already got this part, which is the numerator of the left-hand side. Now let's take care of the denominator of the left-hand side. In order to go from k factorials to k plus 1 factorials, we need to multiply each one of them by k plus 1, meaning that we're going to have two k plus 1s on the denominator of the left-hand side, meaning that in order to not break the inequality, we must have them here as well on the right-hand side, giving us in the denominator of the left-hand side a couple of k plus 1 factorials. So we already took care of the left-hand side of this inequality. Now, another thing that you might notice is that you can rewrite this 2k plus 2 as 2 times k plus 1, meaning that not only we're going to have 2 to the 2k minus 2, but actually 2 to the 2k minus 1 if we multiply this 2 by the 2 to the 2k minus 2. So we're one step closer to the answer. We can also simplify the k plus 1s, and if for some reason we can prove that 2k plus 1 over k plus 1 is smaller than 2, meaning 2 is bigger than that, given that we're on the biggest side, which is the right hand side, we could turn this into a 2, which would give us the 2 to the 2k. Remember, when you have an inequality, either you make the biggest side even bigger or the smallest one even smaller. That's the only way to maintain the inequality. Or you multiply everything by a constant. Also doesn't break the inequality, but it doesn't apply for this specific moment. So now the question is, how can we prove that 2 is bigger than this? If you view this as a function, as a rational function in this case, it has two asymptotes, a vertical one at x equals -1 or k equals -1, and you have a horizontal one at 2. And if you plot this graph, you see that for positive values of k, there's an asymptotic behavior which makes it approach 2 but never touch it. Therefore, 2 is actually bigger than this, meaning that we can replace it by 2. Therefore, by multiplying 2 to the 2k minus 1 by 2, we get to our goal, which is 2 to the 2k on the right hand side. Pretty nice exercise, isn't it? So let's write the conclusion. Given that p of 5 is true and p of k plus 1 is true whenever p of k is true for some positive k, by the principle of mathematical induction, p of n is true for all positive integers greater than or equal to 5. And there you go, two harder exercises which mix induction proofs and inequalities.